Have you ever watched a commercial airliner taxi down a runway and thought about the sheer mass of what you're looking at? Hundreds of tons of metal, cargo, and fuel. Yet, as it gathers speed and leaves the tarmac, it pushes all that bulk into the sky. The physics keeping that metal in the air comes down to a strict rule formulated centuries ago, Newton's third law of motion. It dictates that for every action, there is an equal and opposite reaction. If you want to move forward, you have to push something backward. You've actually tested this yourself. If you've ever blown up a balloon and let it go, the trapped air rushes out and the balloon shoots forward across the room. But lifting a jetliner requires a bit more force than a party trick. A modern aircraft engine has to generate over 100,000 newtons of thrust just to get off the ground. A balloon runs out of air in 3 seconds. An airplane has to maintain that massive backward push for a 14-hour flight. To do that, engineers built a machine designed to contain a continuous, violent explosion that never runs out of breath. The process starts at the very front of the engine, right at the intake. As the plane rolls forward, this wide opening gulps down hundreds of kilograms of raw atmospheric air every single second. But simply funneling air through a tube won't generate thrust. To get a reaction powerful enough to lift a plane, that raw air needs to be forced into an incredibly tight space. That's the job of the compressor. The air hits multiple layers of rapidly spinning blades that violently squeeze it. The volume drops dramatically, while the pressure and temperature spike. All of this crushing force is entirely preparatory. By tacking the oxygen molecules as tightly as possible, the engine creates a highly volatile, dense environment that is perfectly primed to burn. Now, this pressurized air enters the combustion tanks. Jet fuel is sprayed into the dense oxygen and ignited. The temperature jumps to over 1,500 degrees Celsius, creating a sustained, directed explosion that channels raw energy straight toward the back. But right before that superheated gas escapes out the back, it hits the most critical component in the entire machine, the turbine. The rushing exhaust gas forces the rear turbine blades to spin at massive speeds. Because these rear blades are connected by a physical shaft directly to the compressor blades at the front of the engine, the exhaust actually powers the intake. This mechanical loop is what makes the engine work. It actively harvests its own explosive output to pull in more air, compressing and burning it in a cycle that feeds itself indefinitely as long as there is fuel. Once the gas passes the turbine, it blasts out of the exhaust nozzle. The physics remain exact. The faster those gases exit the rear, the stronger the forward thrust pushing the aircraft through the sky. The earliest engineers harnessed this cycle in the form of the turbojet. It was a basic iteration built almost entirely to generate raw, unfiltered speed for early military and test aircraft. But the core loop is adaptable. By modifying the turbine shaft, engineers created the turboprop, using that same rotational energy to spin external propellers, which works well for smaller, slower aircraft. Today, the standard is the turbofan. It takes the sheer power of the central jet core and uses it to turn a massive set of fan blades at the front, balancing heavy thrust with high fuel efficiency and quieter operation. Mastering this mechanical loop changed the scale of human movement. In just a few years, a journey across an ocean that once took weeks by ship was reduced to a 6-hour flight, turning massive continents into manageable day trips. Strip away the metal housing, and the jet engine is simply a continuous, self-sustaining loop. It takes thin atmospheric air and liquid fuel and turns them into enough kinetic energy to lift hundreds of tons straight into the clouds.